In this case, now we want to consider a complex form of normal force, where normal force is not just equal to the weight of the object as considered in the previous video. In this diagram on the board, we are going to look at motion on a slope, as if you're climbing a hill or you're coming down a hill. To do this, we use inclined plane. So this is still like motion along an inclined plane. Please look at the board here. We have this inclined plane. This inclined plane has a body of mass m. So we have this body, the mass is m as usual, okay? And then the mass on this inclined plane, as you see, it can naturally slide down the inclined plane. And then we have a force that is resisting the motion of the mass down the plane. That force is our friction force. The weight of the mass is W equal to mg. This weight is inclined at an angle theta. So we have the x component and the y component of the weight. Because this weight is inclined at an angle, we are going to resolve this weight into these two directions, making this a two-dimensional problem. So resolving this W in x and in what? Y direction. This is our normal force. You can see that the normal force in this case now is not equal to the weight of the body any longer, but it is equal to Wy because it is acting along the same line as the y component or the perpendicular component of the weight of the body. In this inclined plane, what are we going to do? We will determine the normal force. Yes, like you see, the normal force is equal to Wy already. We're also going to calculate the acceleration of this mass along the plane because this mass can slide along the plane. Please take note. In the perpendicular direction, there is no motion. Therefore, acceleration is equal to 0. The reason is because this inclined plane supports this mass. Therefore, the mass cannot fall down this way. It can only slide along the plane. Good. We now want to resolve this W along these two dimensions. How do we handle this? Please, I want you to watch carefully here because this is the part that makes inclined plane a bit problematic to some people. Why? We already know, as many textbooks will say, that if you are resolving in x direction, you use cos, and if you're resolving in y direction, you use sine. But that does not apply here. Why most textbooks say that, well, it's correct, but that is not the actual reason for using sine theta for y and using cos theta for x. The truth is, you use sine theta for the side of the right angle triangle facing the given angle. That is, you use sine theta for the opposite. While you use cos theta for the side not facing the given angle. That is the general reason for using sine in some cases and using cos for resolving in some cases. Now, in this case, what happens? Did you take note that the theta given to us is facing this side of this right angle triangle? Look at it, the theta is facing this side. And we know that this side of the right angle triangle is parallel to WX. So that gives us the x component of the weight. Since the angle is facing the x component, that is WX, you see they are parallel. It means they are the same. It means we are going to resolve along this direction using sine theta because the given angle is facing it. Then when you're now resolving perpendicular to the plane WY, because the given angle theta is not facing WY, is not facing the side WY. WY here is the adjacent. So we use cos theta to resolve in that direction. Before we do that, let's quickly take a look at the free body diagram of this mass. Okay, this is the mass, the particle there. We have these forces acting on it. This is the weight of the object W, which is equal to mg. Okay, then you notice that this is the x component of the weight, this is the y component of the weight, and then we have this angle theta. Along this direction, we have our friction force Fr, and then along the wy direction we have our normal force. Remember that motion only takes place along this direction. So we have acceleration in that direction, but in this direction there is no motion. Therefore, acceleration in the vertical or perpendicular direction will be taken as 0. Good. Having written this, how do we get the Wx value of the weight? So to obtain our Wx will be equal to the weight resolved in x direction here, which has already been explained to be sine theta. So we have Wx to be equal to W sine theta. And of course, you know this is still the same as mg sine theta. Then to get the y component of the weight is going to be W cos theta. And that is still the same as mg cos theta. So we have now gotten the x component of the weight and y component of the weight. At this point, our problem is pretty solved. We are now going to quickly move into applying Newton's second law of motion. And you know that Newton's second law of motion says that the net external force is equal to what? Ma. Good. Let us consider the motion of this mass, which occurs along the what? Plane. You know that along the plane, looking at the free body diagram, we have two forces there, that is Wx and what? Fr. So we're going to write the net external force in terms of these two forces. You know that the mass slides down. So in the Wx, we're going to take it as positive. Frictional force is an opposing force, so we'll take it as what? Negative. If we impute that for the net external force, we are going to get Wx minus frictional force Fr equal to Ma. And this we are going to call equation 1. This is the Newton's second law for this inclined plane system. We want to obtain the acceleration now under two conditions. Case 1, where there is no friction, that is, taking this as a frictionless plane. And case 2, where there is friction. So we move on to our case 1 analysis, where there is no friction, so as to get the acceleration value. Case 1. We assume there is no friction, so friction force will be equal to 0. Using this equation 1, Newton's second law for this system, Wx here will now become what? Wx we know is mg sine theta, so we substitute. Mg sine theta will now be minus Fr, and friction force, there is no friction here, case 1, so this will be 0, equal to Ma. If you make A subject of the formula, you know this is mg sine theta equal to Ma, because this 0 will be neglected, and that will give us acceleration to be mg sine theta divided by m. Therefore, acceleration in an inclined plane when there is no friction will give us g sine theta. This is equation 2 for calculation purpose. The masses we cancel out here, you know. Good. We now move on to case 2. Assuming that the plane has friction. So case 2. If there is friction, we go back to Newton's second law of this system, where we have our Wx minus Fr equal to Ma. We substitute. Wx is mg sine theta. So we have mg sine theta minus Fr equal to Ma. Then making acceleration subject of the formula is going to be mg sine theta minus the friction force, everything divided by mass. And this gives us equation 3. You can see these acceleration formulas, 2 of them, okay? This acceleration of equation 2, where there is no friction, is usually greater than the acceleration in equation 3, where there is friction. Of course, we expect that, because once there is friction, we know that the motion will be what? Reduced. In conclusion, we now look at the normal force. Normal force, as explained here, it is acting on the same line as the y component of the weight. And so that makes n to be equal to wy. And we know wy already to be mg cos theta. Therefore, the normal force is equal to mg cos theta. What does that tell us? That for an inclined plane, the normal force is not equal to the weight of the object, but generally it is less than the weight of the object.